This second screencast is about what causes glaciers to move. Now in this photo you can see obviously a snowball, and we need to know how glacier ice is actually formed. When you make a snowball and you're squeezing that snow in your hands, it becomes hard and solid. Now ice forms at the bottom of a glacier in a very similar way. So what happens is snow falls on top of snow, and each year that snow compresses the previous year's snow, and so it gets harder and harder. The individual snowflakes are compacted into smaller particles of ice which stick together to form larger granules called firn. And then what happens with more snow falling each year, actually it causes the bottom bit to melt and the water refreezes and becomes very hard, and we call it blue glacial ice. What we have in this diagram is what's known as the glacial system, and that is made up of two kind of key parts: the zone of accumulation towards the top of the glacier and the zone of ablation towards the bottom of the glacier, and we'll talk about them in a minute. But on the previous slide what we talked around was this snow that continues to fall on top of snow that's already there. And so the air continues to get squeezed out, we get firn, and then at the bottom of here we'll have blue glacial ice being created. Now what we also have, as you can see on this little bit here, are avalanches of snow and ice that also provide inputs into the system. So the inputs are snow that obviously comes from the sky, but also from avalanches. So we have inputs that are occurring at the top of the glacier here in the zone of accumulation, but we also have the zone of ablation where we have outputs. Now ablation mostly involves melting. This is likely to occur near the snout, which is this bit down here, the snout, or the end of the glacier, where the air temperature is higher, particularly in the summer. So as you can see, the zone of accumulation is very high, so in the top of the mountains here, and as the glacier moves downhill, the temperature, the air temperature is actually going to be rising. So down at this point, down near the snout, the temperature is at its warmest and can potentially be melting that ice. You also, of course, get melting sometimes on the surface of the glacier, particularly during the summer when the temperatures are warmer. Now occasionally chunks of ice can break away at the snout. This is called calving and is another output from the system. A final output is the loss to the air by evaporation, water liquid to water vapour in other words, and sublimation, which is water solid to water vapour. So to try and make that a little bit more simple, obviously when water evaporates from a liquid to water vapour, that's evaporation. But when it is actually a solid form, so when the water is actually in ice and then it evaporates to water vapour, we call that sublimation. So this diagram shows us exactly kind of the same information as what the previous slide has shown us, but what's important is this bit around here. So this ice, as it's coming down the valley, will advance if there's more accumulation than ablation. In other words, if more snow's been added up here in the accumulation zone, then actually it's melting down here in the ablation zone. However, the ice will retreat back up the valley if the ablation is actually greater than the accumulation. So the snout of the glacier melts and the glacier retreats back up the valley. Now we're going to talk about this glacial budget here in a bit more detail in a minute, but the glacial budget, as it says, is the difference between the accumulation and the ablation of ice each year. So it's the difference about the amount of snow that's been added to the amount of snow or ice that's been melted. Now the glacier budget is the balance between the inputs and the outputs. If accumulation exceeds ablation over several years, the glacier will advance, it goes down the valley. If ablation, however, exceeds accumulation over several years, the glacier will actually retreat. Now on this diagram, accumulation tends to dominate near the top of the glacier, whereas ablation dominates at the snout. The glacier budget varies between the seasons, which is shown in this graph. In the winter, there will be a lot of accumulation with little ablation, but in the summer, when it is warmer, ablation will tend to dominate over accumulation. Now what this graph has shown us, this line here, the dark line, is the zone of accumulation. The dashed line, this one here, is the zone of ablation. The blue, where it's shaded, is the negative budget. So in other words, we're getting ice melting. whereas the yellowy-orange colour is positive budget. In other words, the snow is being added. Now, as always, when looking at graphs, it's important that we look at the axes. So along the bottom here, we've got time. So one winter, then a summer, then a winter, then a summer. And up the side, you've got output stroke inputs in metres of water equivalent. So if we take this first winter here on the left-hand side, we can see that the zone of accumulation is far higher than ablation. And so what's happening in this point is that we've got heavy snowfall in the winter and little melting happening. And so the glacier budget, we're actually having a period where more ice is being added. So the glacier has grown and it's actually advancing. In the summertime, we've got a high rate of melting in the summer, so the ablation is higher than the accumulation. And so this here refers to the fact that we're losing ice, so we're actually having ice melt at the snout of the glacier. We're in a zone of ablation. And then obviously during the winter again, temperatures become colder, we get more snowfall, so accumulation takes over again, the ice advances. Then ablation takes back over in the summertime and the ice will actually retreat. Now it's really important that we understand these key terms. So just to go over them again, accumulation here, it's about the inputs to the glacier budget such as snowfall and avalanches, what gets added to it. Ablation are the outputs from the glacier budget such as melting. So when the ice is melting, it's in ablation. The snout is the front of a glacier, the bit where it actually starts melting, where the zone of ablation actually is taking place. And the glacier budget is the balance between the inputs, in other words the accumulation, and the outputs, which is the ablation of a glacier. It's really important that we have a case study of a glacier that we've studied. And this glacier that we're going to look at is the South Cascade Glacier in the USA. And it's found in the state of Washington. And it's one of 3 benchmark glaciers in the USA that have been monitored by the United States Geological Survey, otherwise known as the USGS, for over 40 years. And data has been collected on stream runoff, air temperature and mass balance, in other words the glacier budget. Now all 3 glaciers have shown a marked retreat which may well be caused by global warming. Worldwide, this trend is mirrored by other studies. If we look at the 2 photos here, they show how the South Cascade Glacier has changed between 1928 on the left-hand side and 2006 on the right. And this table down here, Table D, contains some statistics that illustrate the changes that have taken place in the glacier budget between since 1985. So if we just look at these photos for a minute, you can see that the glacier here in 1928 stretches quite a way down the valley. If we compare that to the 2006 one, you can see here the snout of the glacier is far further up. So the glacier has retreated from somewhere around here and it's gone back up the valley due to this area of zone of ablation melting, and the glacier goes back up the valley there and retreats. Now if we look at this table here, although it's not completed, these columns down here, as part of the task in the textbook, we can see very quickly just by looking at the winter meters and compared to the summer meters, and if this here is higher number than that, then we know that we're in the net balance in terms of a negative. The glacier is retreating. So on this first one in 1985, 2.18 meters in the winter, minus 3.38 in the summer. That gives us a net balance of minus 1.2 meters that glacier would have retreated. And as you can see, as we go down here, the numbers continue to be higher all up to 1991. Now in 1991, 3.54 in the winter, minus 3.47 in the summer, means the glacier would have just advanced slightly there. But you can see big retreat in the following year, big retreat in the year after that, big retreat again, big retreat again, and again not until we get to 1996 where the winter figure is higher than the summer figure. So the glacier would have advanced in these 2 years, then retreats again, advances in 1999 and again in 2000, retreats a long way in 2001, advances slightly in 2002, retreats a big way in 2003, retreats again in 2004, retreats in a long way in 2005. So you can see that the glacier over time is retreating. The summer meters are higher than the winter meters, which means that glacier is continuing to retreat back up the valley.